Good morning. We're here for the second half of day 5. So this is going to be section 3.1, introducing the derivative. Now, this might seem scary just because it's a new word, or maybe you haven't taken a calculus class before, but don't worry. The derivative is an easy concept once you've mastered section 2.1. We're going to relate it back to that, so you're going to have a nice foundation to stand on. So last time we calculated the slope of the tangent line, and we used the average rate of change of f on the interval a to x, and we said that that's the slope of the secant line. So slope m, secant for secant line, is f of x minus f of a divided by x minus a, while the instantaneous rate of change in f at a is simply the limit of the secant line, and that's how we get the slope of our tangent line. So this equation, m subtangent, which is the slope of our tangent line, is equal to the limit of x approaching a of f of x minus f of a divided by x minus a. And this is the slope of our tangent line at a comma f of a. And we have to assume that the limit exists. So if the limit does not exist, then there is no slope at this tangent line. So just like before, we have our graph where we've got a distance between a and x. And you might be saying, Emily, you switched a and x, and that's just for notation purposes. But we can call the distance between a and x this value h. Let me get my pointer up. So we can call this distance between a and x some value h. It doesn't matter if it's 1, it doesn't matter if it's 50, it's just the distance between a and x. That means that a is just a, and x can be defined as a plus the distance h. And that's how we get to this new definition over here on the right-hand side of your screen. Well, with a new definition, a new reimagining of what we're calling our variables, we get a new definition for the rate of change and the slope of the tangent line. So the average rate of change of f on the interval a to a plus h, which we just saw is the same as a and x, is the slope of the secant line. So we have m secant equals f of a plus h minus f of a divided by my x value, which is a plus h minus a. Well, that just boils down to f of a plus h minus f of a, all divided by h. So the instantaneous rate of change in f at a is the slope of our tangent line, provided the limit exists. It's the limit as h approaches 0, right? We want that distance between x and a to go to 0, of f of a plus h minus f of a divided by h. So we saw an example in the previous lecture with x's and a's. So let's look at an example with h's and a's. So here's my example. Find the slope of the line tangent to the curve f of x equals x cubed plus 4x at the point 1, 5. I am going to ask you to pause, maybe take a breather, get some water, and work through this and see as far as you can get. If you can't get too far, then go ahead and proceed. All right, back from our break. So from our most recent definition, we have the slope of the tangent line is the limit as h approaches 0 of f of a plus h minus f of a, all divided by h. Our h in this case is the value 1, so we can plug that in. We have our equation x cubed plus 4x, and we substitute h plus 1 in for x, and we know that f of 1 is just equal to 5. So we plug all of that in, we expand out h plus 1 cubed, and we get h cubed plus 3h squared plus 7h plus 5 minus 5. So these 5s are going to cancel each other out. Well, when the 5s cancel each other out, everything in the numerator has an h in it, so we pull that h out. H divided by h equals 1. That doesn't matter anymore. So now we just have h squared plus 3h plus 7. We're taking the limit as h approaches 0. So I've got 0 plus 0 plus 7. So the slope of our line tangent to the curve is 7. So finding the slope of a line tangent to a curve f at a point A is a huge concept, and it's pretty much what the entire course is based upon, and it's the idea of this thing called the derivative. The derivative is the same as the slope of a line tangent to a curve. If you want to think about it as the slope of a line tangent to a curve, if you want to think about it as m subtangent, if you want to think about it as instantaneous velocity, All of that jives with me. You just have to remember that all these definitions are interchangeable. And we use the derivative because we're talking about math. You'll see this idea again and again in a physics class, maybe in a chemistry class. I'm not sure. I almost got a physics degree, so I'm more familiar with that. So let's talk about the derivative. And we can take the derivative of a function at a point. So the derivative of my function f at a point A is denoted f with one apostrophe, parenthesis a, close parenthesis. And this is typically called f prime of a, or the derivative of f at a. And it's given by the following definitions. So we can do it in our x and a domain. So f prime of a is equal to the limit as x approaches a of f of x minus f of a divided by x minus a. Or we can do it in the HA regime. So f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a over h. And if f prime of a exists, i.e. the limit exists, we say that our function f is differentiable at a. And the entire study of Calculus 1 is differentiable calculus. Calc 2 is integrable calculus, but Calc 1 is about differentiable calculus. So we can take limits, we can find continuity, and now we're going to be able to take derivatives at points. So let's work through an example. And this one might be a little bit much, but that's okay. So let f of x equal the square root of 2 times x plus 1. And I want you to compute f prime of 2. So the derivative of f at x equals 2. So go ahead and take a pause and see if you can at least set it up, if not get a few steps down. If you can, amazing. If you can't, that's okay too. We're going to walk through this example. So here's our example. Let's start by using our first definition of the derivative. So this one is going to be in terms of x's and a's. So I have f prime of a is equal to the limit as x approaches a of f of x minus f of a divided by x over x minus a. This equation should be familiar. It's the slope of the tangent line. So now we're going to plug in our value 2. So the limit as x approaches 2 of f of x minus f of 2 divided by x minus 2. Now we plug in our function. So I've got the square root of 2x plus 1 minus f of 2, which is just positive 3, divided by x minus 2. And I'm left with the limit as x approaches 2 of the square root of 2x minus 2 divided by x minus 2. Now, just because I want to have some algebra fun, we're going to continue on with this. It takes 2 pages for this example, and that's okay. So now we're going to multiply by the conjugate of the square root of 2x minus 2, which is square root of 2x plus 2. So we have our original equation, and it's now equal to the same thing we had from the very last step times square root of 2x plus 2 divided by the square root of 2x plus 2. So I've got something on the top that's the exact same as something on the bottom. Divide those out, you get times the number 1. So I haven't really changed my equation too much. Once you factor everything out, you just get 2 times x minus 2 on top divided by x minus 2 on bottom times square root 2x plus 2. And I should add in another set of parentheses. So our x minus 2 terms are going to cancel out, and we're left with 2 divided by square root of 2x plus 2. Well, let's go ahead and take our limit as x approaches 2, and now we can just plug everything in. So when we plug everything in, we get 2 on top and 4 on the bottom, which is the same as 1/2. So the derivative of our function f of x at the point x equals 2 is equal to 1/2. All right, so that's it for today.